This screencast demonstrates how requirements modeling and analysis can be carried out in the SeCMER tool. The SeCMER tool offers smooth integration of existing requirements modeling formalisms, support for argumentation analysis with change impact analysis, and incremental checking of static security properties over requirements models. Requirements in the SeCMER tool are captured in the C* notation. C* offers a rich graphical notation for capturing system-level requirements in an early phase of design. In our running example, there are two actors, the arrival manager, shortly AMAN, and the Meteo data center. The Meteo data center provides the resource Meteo data and hands it over directly to the arrival manager. The arrival manager has a security goal to protect the integrity of this asset. The arrival manager trusts the Meteo data center over the fulfillment of this goal. Finally, the arrival manager conducts security screening to check the employees. While the C* notation provides input for requirements engineers in a graphical way, not all the details of a requirements model can be easily represented graphically. For this purpose, there is an alternate representation of the same model. The SeCMER conceptual model offers a unified, abstract representation for requirements, which can also be captured using the textual syntax. Next, we demonstrate how changing the requirements model will trigger bidirectional synchronization between the C* and SeCMER notations. For this purpose, we introduce a plan change. For instance, we come up with a new component called System-Wide Information Management. The change introduced to the C* model triggers incremental and bidirectional model synchronization, guided by change-driven transformations. Changes can also be introduced directly to the SeCMER model. For instance, we can reroute communication through the SWIM. As a result, this change also causes synchronization between the models. After numerous additions, the new C* model constitutes the post-state of the planned change. The resource Meteo data now passes through the SWIM component. The SWIM network and two SWIM boxes were introduced in the model to represent this new communication path. And a new security goal is added. Next, we demonstrate how to automatically detect violations of static security properties like untrusted delegation. Here in our example, the resource Meteo data is communicated along three actors, the SWIM component and the two SWIM boxes. The arrival manager does not trust them, so they violate the arrival manager's security goal, Meteo data integrity. The violations are automatically detected using security patterns and evolution rules. Here you can observe the formal description of the security pattern. This is defined in the language of the Viatra model transformation tool, and it is incrementally evaluated using EMF-IncQuery. The SeCMER tool also offers quick fixes to automatically resolve the detected security violations defined by evolution rules. Here in our example, there are three detected violations as the Meteo data goes through three untrusted SWIM actors. We can select automatic suggestions. In the first solution, the arrival manager trusts the SWIM to handle the resource well. The second solution is that the arrival manager trusts the SWIM to handle the resource well with respect to this integrated security goal only. And solution 3 uses a digital signature system so that an untrusted path is no longer a problem. So let's select solution 1. Now a trust link has been inserted to the model, but there are still two more untrusted actors. However, as they are components of the SeCMER, we can assume that they are trusted by the SeCMER network and thus transitively by the arrival manager as well. So we manually introduce the corresponding two trust relations to the model. And as a result, all the security issues have been resolved. Argumentation analysis aims to reason about the security of the system and to incrementally assess the impacts of change. In our example, the satisfaction of the security goal is supported by an informal argument. The argument model records an argumentation process performed by a board of security experts. The argument model consists of a root claim about system security, elementary facts the root claim is based upon, implications of these facts, rebuttals challenging the root claim, and mitigations against the rebuttal. Our sample argument relies on the fact that the arrival manager conducts security screening of its employees. It is referring to the adapter arrival manager carrying out the action security screening via traceability links. Let's now explore a design alternative that aims to save cost by omitting the security screening of employees, therefore deleting it from the model. As a result, the tool detects that the change may invalidate the informal argument model, so therefore the argument will have to be reconsidered by the experts.